All right, so today we're going to take a look at some of the rules and properties for dividing exponents. So we're going to be taking expressions and simplifying them by applying these rules. We're going to be looking at both division properties with exponents as well as what happens with zero exponents and negative exponents. So we'll be finding the quotient of two expressions, two monomials, and we'll simplify expressions by division, as well as those expressions that contain negative exponents and zero exponents. So our first property here is, if you remember back to the last video on multiplying with exponents, what we're going to be looking at today is we're dividing. So that's what this word quotient comes in. Quotient obviously means to divide. So the first rule that we're looking at is what happens if we divide two powers with the same base. Okay, so if you remember, the product of powers talked about what happened if we were multiplying powers with the same base. So if we had x squared times x to the third, right? Since we're multiplying powers with the same base, what we would do is we would add the exponents together. We would have a total of x to the fifth power. Okay. Well, the opposite of multiplication is division. So since the opposite of a product is a quotient, it makes sense that what we're going to be doing is, instead of adding exponents together when we divide, we're going to be subtracting the exponents. So let's take a look at why we're able to do that. So if we take this first example, c to the 11th power divided by c to the 8th power. Okay. And remember back what an exponent is. It's got a base and an exponent. The base is what's being multiplied, and the exponent tells us how many times to multiply it. So c to the 11th power means we're multiplying c 11 times. 6, 7, 8, 9, 10, 11. All right, so we've got 11 c's here in the numerator. And in the denominator, we've got c to the 8th power. So that means we're multiplying c 8 times in the denominator here. Make sure that's 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, so now let's think about what does it mean when we have a fraction? Well, anytime, if we were to have c divided by c, right, anything divided by itself simplifies to 1. Right? So think back to what we know about fractions. When we have the same value in the numerator and the denominator, they cancel each other out and they become just 1. So here I've got c and c, so I can cancel those out and they become 1. And I can do that with every set of c's that I have, as long as there's 1 in the numerator and 1 in the denominator. So as we go through here, sort of canceling out pairs. So every time I cancel one out on the top, I've got to cancel one out in the bottom until I get down to this last one, and what happens? I ran out of c's in the denominator. Right? All that's left, I canceled all those c's out, so all we have left is 1. Okay? Same thing in the top here. I've got all these c's here, but they've all been canceled, so it's just 1. So how many c's are actually left in the numerator? Well, there's these right here. There's 3 of them. So in the numerator, I've got c to the 3rd power. In the denominator, I have no more c's, I just have 1. So c to the 3rd over 1 is just c to the 3rd. So is there a shortcut, rather than having to write out all of these c's every time we want to divide powers? Is there a shorter way that we can do it? And there is. When we're dividing powers with the same base, what do you see here? C to the 11th divided by c to the 8th. Well, if I only have 3 left, what did I do? I took c to the 11th and I took away those 8 from the bottom, and what was left was c to the 3rd. So I subtracted the exponents. Right? And you'll see it with this other example here. If I take r to the 5th and I'm dividing by r squared. So notice these powers have the same base, r, right? We're repeating the variable r 5 times in the numerator, 2 times in the denominator. So when I cancel out the like ones in the top and the bottom, what's left is r to the third. And that's the same thing as if I had taken those 5 in the top and took away the 2 from the bottom. Okay. So anytime we're subtracting powers that have the same base, and again, they have to be the same base, we subtract the exponent from the numerator minus the exponent from the denominator. And that's important. It has to go the numerator minus the denominator. So whatever's in the numerator, I have to subtract the numerator minus the denominator. Otherwise, it's going to change my value. Right? All right, so let's simplify this expression. X to the 7th, y to the 12th, divided by x to the 6th and y to the 3rd. So the first thing that I notice is that there are 2 different sets of exponents here, or 2 different sets of expressions. I've got x's, x to the 7th, and x to the 6th, and then I've got y's, y to the 12th and y to the 3rd. So what I do is I want to kind of split them up and deal with them separately, because again, I've got to deal with bases that are the same. So if I've got x to the 7th and I'm dividing by x to the 6th in one expression, the other one's going to be y to the 12th divided by y to the 3rd. So to simplify this, since I'm dividing powers with the same base, I can subtract the exponents. So x to the 7th divided by x to the 6th, I can take x and just do 7 minus 6. Right? For y, I'm doing y to the 12th divided by y to the 3rd, so that can be y to the 12 minus 3. So what's left when I do those subtraction? X to the 7 minus 6 is just x to the first power. Y to the 12 minus 3 is 12 minus 3 is 9, so it's y to the 9th. And I don't have to write this as x to the first, I can just write this as x times y to the 9th power. And that would be this original expression, x to the 7th, y to the 12th, divided by x to the 6th, y to the 3rd, simplifies to x times y to the 9th. Right, so take a minute and try this one on your own. Simplify a to the 3rd times b to the 9th divided by ab squared. Should have gotten a solution a squared b to the 7th. And again, I'll quickly go over that with you. So what you can do, you've got a's in both the numerator and the denominator, so take those expressions. So you're going to be a to the 3rd divided by a. And b, you're doing b to the 9th divided by b to the 7th. So just subtract the exponents. Since we're dividing powers with the same base, I just subtract the exponents. So a to the 3rd divided by a. And remember, since there's no exponent there, just understand there's a 1. So it's 3 minus 1. And for b, we're doing 9 minus 7. So then it's just a matter of subtracting. So 3 minus 1 means I have a squared. And that was a mistake. b, 9 minus 2. Sorry. So 9 minus 2 is b to the 7th. All right, I'm not going to spend too much time on this one because this kind of follows the same idea as when we did the power of a power. And the power of a power, or the power of a product, said when we had a product, like for example, AB, and we raise it to an exponent, let's say to the 4th power. Right? Each part of the product gets that exponent. It's a to the 4th, b to the 4th. In the same way, if you have a quotient or a fraction, so we're dealing with a quotient again, the power in both the numerator and the denominator is the same as the entire thing. Okay, so find the power of the numerator and the power of the denominator. So if I take 3/5 here and I raise it, the whole thing to the 4th power, I'm doing 3/5 to the 4th power. Well, what is that? That's 3/5 4 times, right? So 3/5 times 3/5 times 3/5 times 3/5. Well, if I want to write this back as one expression using exponents, how many times am I multiplying 3? I'm doing 3 to the 4th power. And on the bottom, I've got 5 to the 4th power. So notice all I did was I took the 4 and I raised it shared it with both the numerator and the denominator. It became 3 to the fourth and 5 to the fourth. Right? Same thing if I were to take the second one here, r over t to the fifth power. Well, then that's like doing r over t 5 times. Right? R over t, that's 4 and 5 times. So how many r's do I have altogether? In the numerator, I have r to the fifth power, and in the denominator, t to the fifth power also. So it's just a matter of sharing that exponent with both the numerator and the denominator. So if you have a fraction, make sure that if the entire thing is in parentheses and raised to a power, you share that power with both the numerator and the denominator. So if we look at the example, 4c to the third d squared divided by 5 and then raised to the third power. So if I take the whole thing, 4c to the third d squared divided by 5. The entire thing is being raised to the third power. So the rule that we just saw was that if I've got a fraction or a quotient raised to a power, I need to share that power with both the numerator and the denominator. So when I rewrite this, it's important that I keep these parentheses in mind. So this whole numerator is 4c to the third d squared. That whole numerator is being raised to the third power. And the denominator, all I have is 5. So 5 is also being raised to the third power. So now we've got in the numerator, we have one of the properties from when we're multiplying exponents. We're raising this product, 4c to the third d squared to the third power. So that means 4 is being raised to the third power. C to the third is being raised to the third power, and d squared is being raised to the third power. So let's show what that looks like. It would be 4 to the third. C to the third raised to the third power means I'm going to multiply 3 times 3. And then d squared to the third power means I'm going to do d to the second times 3. And that's all over 5 to the third. So now it's just a matter of simplifying. 4 to the third power, we could rewrite that. 4 times 4 times 4 is 64. C to the third, and then if I do 3 times 3, that means I have c to the ninth power. And d squared to the third power is d to the sixth. And then in the denominator, 5 to the third, well, 5 times 5 is 25. 25 times 5 is 125. So this is the expression 4c to the third d squared divided by 5 raised to the third power. Notice it's the numerator raised to the third power and the denominator raised to the third power. All right, so go ahead and try simplifying this one. Take that fraction, 3m to the third n squared divided by 4p to the fifth q, the entire thing raised to the third power. And you should have gotten an answer for letter B. So again, just to quickly walk through that, because we are doing a fraction raised to a power, I can raise both the numerator to that power and the denominator to that power. So 3m to the third n squared raised to the third power. And then the denominator, I've got 4p to the fifth q, also raised to the third power. So I just need to remember that because both the numerator and the denominator are products, I need to share the power that's in the numerator with all the parts of the numerator. I need to share the power in the denominator with all the parts of the denominator. Okay. So that becomes 3 to the third. M to the third, m to the third raised again to the third power means I'm going to multiply 3 times 3. And then n squared raised to the third power is 2 times 3. In the denominator, I've got 4 to the third. Then when I do p to the fifth 3 times, I'm going to multiply 3 times 5. And then q, again, there's a power of 1. So I'm going to do 1 times 3, which should give me a final answer of 3 to the third is 3 times 3 times 3, that's 27. M, if I do 3 times 3, that's 9. N, 2 times 3 is to the power of 6. And in the denominator, 4 to the third power is 64. P 5 times 3 is to the 15th power, and Q 1 times 3 is to the 3rd power. So your final answer should have been 27 m to the 9th, n to the 6th, divided by 64 p to the 15th, q to the 3rd. And because none of the variables in the numerator and the denominator have the same base, I can't simplify it anymore. 27 and 64 don't have any common factors, so I can't simplify it. So this would be my final answer here. Okay, so now we've come to the zero property, and this is important. It's actually pretty simple, but there's a couple of proofs behind it that we can go over. But the main idea is that for any non-zero number raised to the power of 0, it's equal to 1. And this says number here, but keep in mind that this could be variables also. So anything that's not 0 raised to the 0 power is equal to 1. Basically this rule here, a to the 0 is 1. So that means that 15 to the power of 0 is 1. Right? So 15 to the power of 0 is 1. B over C, if I take this fraction, B over C, right? Well, the rule that we just saw was that if I have a fraction, a numerator and denominator raised to a power, I raise both the numerator and the denominator to that power. Well, anything to the power of 0 is 1, so B to the power of 0 is 1, C to the power of 0 is 1, so the whole thing is just 1. Same thing, 2/7. If I took 2/7 to the 0 power, well, 2/7 to the 0 power is just 1 also. Anything, any variable, any number that is not 0 raised to the power of 0 becomes 1. And let's look at just quickly why that is. So think about what exponents tell us. So let's start with 4 to the 3rd. 4 to the 3rd means we're doing 4 times 4 times 4. Right, which is 64. 4 squared is 4 times 4, which is 16. 4 to the 1st power is just 1 4, which is 4. So what would 4 to the power of 0 be? Right. A lot of people are tempted to say 0, but look carefully at what's happening in this pattern. So what's happening here? I'm decreasing my exponents by 1 each time, right? I'm dropping down 1 power each time. 3 minus 1 is 2, 2 minus 1 is 1, 1 minus 1 is 0. Right? Every time I do that, what's happening to my final answer here? 4 to the 3rd power, 4 times 4 times 4 is 64. 4 to the 2nd power is only 4 times 4, so I lost one of those 4s. So I divided 64 by 4 to get 16. 4 to the 1st power is 1 less 4, so that's dividing by 4. Well, what would the next one be? If I'm at 4 and I divide by 4, that means that 4 to the power of 0, if this pattern is true, should be equal to 4 divided by 4, which is 1. And that's why anything to the power of 0 is 1. So you can see it as we follow this pattern. Let's use what we learned about dividing exponents in order to do this also. So let's take this first example here, 15 to the power of 0. And what we learned was that if we are dividing powers that have the same base, we can subtract those exponents, right? Well, how can I make 0? I can make 0 by subtracting, let's say, 1 minus 1, right? 15 to the power of 0 is the same thing as saying 15 to the 1 minus 1 power, right? 1 minus 1 is 0. So if I had 15 to the 1 minus 1, I would rewrite that as 15 to the power of 0. Well, how could I write 15 to the 1 minus 1? Well, what do I know? I know that if I have powers that have the same base and I'm dividing them, then I subtract the exponent. So if I had 15 to the 1st power divided by 15 to the 1st power. Let's think if I was working this way in a problem. 15 to the 1st divided by 15 to the 1st. I would write that as 15 and then subtract the exponents, 1 minus 1, and that would give me 15 to the 0. So we're kind of working backwards here. We're starting at the end and we're going back to the beginning. So if we were here and we worked this way, you would be able to do these steps and get 15 to the power of 0. Well, what is 15 to the first divided by 15 to the first? It's just 15 divided by 15, which is anything divided by itself is 1. So 15 to the first power is equal to 1. And so we showed that two ways. We showed it by following this pattern here with exponents. As we're decreasing our exponents, we're dividing by the number that is in the base. So that when we have 4 to the first power, and then I go to the 0 power, I'm doing 4 divided by 4, which is 1. You can also see it based on what we did with our properties of dividing exponents. Right? If I had 15 over 15, that's 1. Well, I can also show that as 15 to the first divided by 15 to the first. Subtract those exponents, which gives me 15 to the power of 0. So this and this are the same thing. So those are two ways to think about why anything to the power of 0 is equal to 1. So let's simplify this expression. 12m to the 8th n to the 7th, 12m to the 8th n to the 7th over 8m to the 5th n to the 10th, the whole thing raised to the power of 0. Well, we know this is a fraction raised to a power, so that means the numerator could be raised to a power, 12m to the 8th n to the 7th raised to the power of 0. And the denominator, 8m to the 5th n to the 10th raised to the power of 0. And then because the numerator and the denominator are products raised to a power, I'm going to share that power with each part on the inside. So 12 to the 0, m, we're going to do 8 times 0, n, we're going to do 7 times 0. And in the denominator, 8 to the 0, m, we're going to do 5 times 0, and n is going to be 10 times 0. Well, anytime I multiply all of these by 0, they're all going to come out to 0. And what we just saw was that anything to the power of 0 is 1. So 12 to the 0 is 1, m to the 0 is 1, n to the 0 is 1, 8 to the 0 is 1, m to the 0 is 1, and n to the... So the entire thing simplifies just down to 1. And I showed you all these steps here. You don't have to go through this every time. The shortest thing is to say that this entire fraction is raised to the power of 0, so the entire thing is 1. Kind of like when we did 2/7 to the 0 is just the entire thing raised to the power of 0. But I wanted you to understand like why each part would be equal to 1. But once the entire thing is in brackets here and then raised to the power of 0, the entire thing is equal to 1. Okay, so now this one, if I take m to the power of 0, then n to the 3rd over n squared. Okay. For this one, notice the only thing that's being raised to the power of 0 is the m. So m to the power of 0 is 1. Then what do I have here with the n's? I've got bases that are the same. They both have a base of n. So I can subtract the exponents. And I'm going to do the numerator 3 minus the denominator 2. So 1 times n to 3 minus 2 is just 1. So 1 times n to the first actually is just n. So in this case, I only had m raised to the power of 0. Right there, right there. So that was the only thing that becomes 1. The n's I needed to simplify using what I know about dividing powers. So I subtracted the exponents there. And so I simplified all the way down to n. All right, so try this one on your own. And this is like that first example that we did, right? This entire thing here, 3x squared y to the 9th over 5z to the 12th. Well, the entire thing is raised to the power of 0. So the entire thing just simplifies to 1. All right, so try this one. Simplify x to the 0 times k to the fifth divided by k to the third. And that should have gotten you d, or k squared. And again, that's because just in here, just the x term has a power of 0. So x to the 0 is 1, then you're going to multiply it times k, and because they have the same base, I can subtract 5 minus 3, so what's left is just k squared. All right, so now we're on to our last property, which is the negative exponent property. And what the negative exponent property says is that anything except 0, so numbers and variables, anything that has a negative exponent, okay, we can rewrite it as a positive exponent by using the reciprocal. And remember what a reciprocal is. So if I have a fraction, x over y, the reciprocal is y over x. So I just flip the numerator and the denominator. Okay. And what the negative exponent property says is that if I have an exponent, 2 to the negative fourth power, I want to write these exponents using positive numbers. So 2 to the negative fourth power, I need to write it as the reciprocal. Well, this is 2 to the negative fourth over 1. So the reciprocal would be 1 over 2 to a power. Now when I flip this fraction, when I flip 2 to the negative fourth over 1, the negative 4 becomes positive 4 when I move it to the denominator. Right? And the opposite would work the other direction. So if I take 1 over j to the negative fourth, I want to write that as a positive exponent. So I'm going to write this as the reciprocal. So it's going to be over 1, and then j moves to the numerator. When I move it up, it becomes positive 4. So 1 over j to the negative fourth would be j to the fourth over 1, or just j to the fourth power. Now, why does that work? Well, let's think back to what we know about dividing exponents. So let's say x to the third divided by x to the fifth. So remember what I said about making sure that when you subtract these powers, you always do the numerator minus the denominator. And this is why. Because when I subtract 3 minus 5, I end up with what? Negative 2. So if I have x to the third divided by x to the fifth, and I subtract 3 minus 5, I end up with x to the negative 2 power. Well, how else could we do x to the third over x to the fifth? Well, when we first learned this property at the beginning of the video, we wrote out these terms, right? X times x times x, and then the denominator x times x times x times x 5 times. Okay? So if I start canceling out these x's, x cancels there, 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 I end up with, in the numerator, that's where everything goes to 1. In the denominator, I still have 2 x's. So how would I write this out? It would be 1 over, what's left? X to the second power. And notice this here, x to the negative 2, and 1 over x squared, both started from the same problem, x to the third divided by x to the fifth. So what we could say is that x to the negative 2 is the same thing as 1 over x squared. Right? And again, so anytime I have a negative exponent, I make it positive by using the reciprocal of that fraction. So x to the negative 2 is actually x to the negative 2 over 1. So I flip that fraction and make the exponent positive. Notice the base doesn't change. X is still the base no matter what. It's just the exponent that's changing. Right? If I go back to my examples here, 2 doesn't change. 2 is still the base. What changes when I flip the fraction is the negative 4 becomes positive 4. Here, j doesn't change. Just when I flip it, the negative becomes a positive. So let's work through this problem here to see how this works. So here we've got x to the negative fourth, y to the ninth, and z to the negative sixth. So I have x, y, and z. I don't have any common bases that I can simplify in both the numerator and the denominator. Right? So the easiest way to do this is to actually break each of these terms apart, x, y, and z, and write them as fractions because I know I'm going to have to change these negative exponents into positives, and it's easier if I can see what those fractions are. So first I have x to the negative fourth, and as a fraction, that's x to the negative fourth over 1. Okay. Then I have y to the ninth, and as a fraction, that's over 1. And z is in the denominator, so z to the negative 6 is in the denominator, which means it's going to be 1 over z to the negative 6th. So now I want to write each of these parts of this fraction here as positive exponents. So I want to take x to the negative fourth over 1 and make it a positive exponent. So I'm going to flip the fraction, so it's going to become 1 over x. My base doesn't change, but the negative 4, when I flip it down, becomes positive 4. Okay. Y to the ninth over 1 is already positive, so I'm not going to mess with that. And z is to the negative 6. So I want to make it positive. I need to flip it up. So z is going to go to the numerator. Again, z doesn't change. My base doesn't change. But the negative 6 is going to become positive 6. And the 1 goes to the denominator. So now let's recombine all of those parts to write it as just one expression. So on the numerator, 1 times z times y to the ninth times z to the sixth would be y to the ninth times z to the sixth. And in the denominator, I've got x to the fourth times 1, so just x to the fourth power. So all I did for this one is to rewrite the expression so that I have positive powers. So the negative exponents moved down, the negative exponent in the denominator moved up, and y to the ninth stayed in the same place because it was already positive. So it became y to the ninth, z to the sixth over x to the fourth. All right, let's take this tricky looking one here. So same idea, but in this case, what I've got is I've got numbers that I can combine. I've got these p expressions here. I've got the q's here, and then I've got an r hanging out here at the bottom by itself. So let me break this apart and keep the common bases together. So the first thing is I've got 75 over 15. Then I'm going to write the p's as one fraction. So that's p to the third over p to the fifth. Then q is to the negative fifth over q to the negative fourth. And r, since there's no other r term in the numerator, it's going to be 1 over r to the negative eighth. Right? So now let's rewrite all of this whole expression here and simplify what we can. So 75 divided by 15, well, that's 5. If I want to simplify p to the third over p to the fifth, I need to do, since they both have bases or p, I'm going to subtract 3 minus 5. Q, negative 5 minus negative 4. This, until you get used to it, it's very important that you actually write out the math and the subtraction that you're doing. And this is why, because a lot of people see negative 5, negative 4, and come up with negative 9. But notice what we're doing is we are subtracting. We're doing negative 5 minus negative 4. And if you write it out this way, you'll make a lot fewer mistakes until you get used to it. Then 1 over r to the negative eighth, well, I can write that as r to the eighth positive 8 over 1, or just r to the eighth. So this whole thing right now is over 1, right? I moved everything up to the numerator in order to simplify these variables. So 5, p has 3 minus 5. So when I do 3 minus 5, I end up with negative 2. Q, if I do negative 5 minus negative 4, that's like adding. Right? Subtracting a negative is adding, so negative 5 plus 4 is negative 1. And hopefully now you see why it's important to write out the math that you're doing so you don't make simple mistakes. And then r to the positive eighth. And again, that's all over 1. Now I need to get rid of these negative exponents and make them positive. So anything that's negative is going to get flipped. It's going to move down in this case. So p to the negative 2, q to the negative first moves down. 5 has a positive power, so it's staying up. r to the 8th is positive, it's staying in the numerator. Then the denominator, I've got p squared and q. So this is what the expression looks like after we simplify it. 5r to the 8th divided by p squared times q. And we got that by taking a little bit of everything that we've done. We subtracted powers with the same bases when we were dividing. R to the negative 8th became R to the positive 8 when we moved it up to the numerator. And so R to the negative 8 here moved up and became positive. And then once we ended up with positives and negatives, right here, P negative 2, Q negative first, we move those down to make them positive. All right, so you go ahead and try this one. Take a minute, simplify this expression so that none of the exponents are negative. You should have gotten a b to the third, c to the fifth over a squared. So this one's pretty straightforward. A to the negative 2 becomes 1 over a squared. B to the third is already positive, so it's b to the third over 1. And then c to the negative fifth, or sorry, it should be 1 over c to the negative fifth becomes c to the fifth over 1. So when I combine all these together here, I've got b to the third and c to the fifth in my numerator, a squared in my denominator. All right, take this expression here. Here you've got some common bases that you're going to need to simplify and then write your final answer so that none of the exponents are negatives. You end up with a final answer of d4 xy to the 6th over z to the 3rd. And what you're going to want to do is just break this apart and then take each part and simplify what you can. So 36 over 9 is one part. X to the 5th over x to the 4th. Y to the 8th over y squared. And z to the 3rd over z to the 6th. So 36 over 9 is simply 4. Then we're going to subtract the powers for x, y, and z. So x, we're going to subtract 5 minus 4. Y, we're going to subtract 8 minus 2. And z, we're going to subtract 3 minus 6. So that gives us 4. X is to the 1st. Y is to the 6th. And z, when I do 3 minus 6, I get negative 3. Right? So if this whole thing is over 1, if I want to make z to the negative 3rd positive, that's my only negative exponent, I need to make it positive, I need to move it down to the denominator. So it simplifies to 4xy to the 6th over z to the 3rd power. All right, and here's a summary of the three things that we talked about here. For dividing powers with the same base, such as c to the 11th over c to the 8th, just subtract the exponents, because what we saw was that when we wrote this all out, a whole string of c's in the numerator and the denominator, when we cancel them, all right, we're eliminating 8 altogether, so we end up with just 3 in the numerator. For the 0 exponent, anything raised to the power of 0 is 1, and if we have parentheses raised to the power of 0, everything in those parentheses becomes 1. And then lastly, we looked at negative exponents, and negative exponents, the only thing that's different is the location. So negative exponents in the numerator become positive by moving them to the denominator. So 2 to the negative 4th would be 1 over 2 to the positive 4th. The main thing to keep in mind here is that the base doesn't change, it's still 2 in both expressions. Right? If I have negative exponents in the denominator, they become positive by moving them back up to the numerator. Okay, so you can kind of see them written out here. A to the negative n is written as 1 over the reciprocal of a to the n, so 1 over a to the n. And then if it's 1 over a to the negative n, it gets flipped, and it's a to the positive n over 1.